Kinematics is the mathematics and geometry of moving objects. So the study of kinematics would be essentially the study of position as it changes over time, the rate at which it changes over time, which is called velocity, and the rate of that rate, which is called acceleration, and the types of trajectories and curves you can expect in space from given circumstances involving those variables. Um, This is where you're going to see quite a lot of calculus in this class because I'm talking about velocity as a rate of change of position, and of course that is a derivative. So we're going to start out by just kind of defining our basic terms and what the relationships are between these variables. So uh, here I have a moving object depicted in this color here. And so this object is here at T1, T2, T3, T4, T5, T6, and T7. Those are just 7 different times. And the idea is this object is moving on some trajectory through space, and we can track the position of that object with vectors. So what we do is we pick some origin, which is arbitrary, you just have to pick one, and from that origin you draw a vector that points at the object of interest. Okay? And over time, as the object moves, this vector is going to have to change the direction in which it's pointing, and it's going to have to change its length to continue to point at that object. So here I have a position vector represented by the letter r, lowercase r, and I've drawn the position vector at time 1, time 3, and time 5. And you can see the position vector initially is pointing up and to the left, and then as the object moves up and to the right, the position vector has to get longer and tilt over in order to continue pointing at that object. Um, so, in kinematics, we describe the position of a moving object using a position vector called r, which points from some origin, the origin is arbitrary, but you have to pick one, to the position of the object at different moments of time. This vector r is a function of time, or a function of t. If you were to use coordinates, which is also a perfectly good way for describing the locations of objects, the position vector r is related to those coordinates in that its components in that coordinate system will be the coordinates of the object. So the x component of r we would call rx, the y component we would call ry, and its components would just literally be the coordinates of the object. As an object moves, we say that each motion of the object through space is a displacement. So I have 3 displacements drawn here, which are from some initial position to a final position. And you can see that we get from the initial position vector to the final position vector by adding, tail to tip, subsequent displacements together to get the total change in position. So I would call the total change in position to be the final position minus the initial position. And that total change is obtained by adding up the individual displacements from the first displacement to the last one. And when you do those, you get the overall change from the initial position to the final position. Now, these displacements can happen over time at different rates. So for instance, maybe this one could hypothetically be very fast, and this one could hypothetically be very slow. And we want to be able to account for that in our description of motion. It's not good enough just to say what path something took. It absolutely matters to talk about how long it took to do so. And so for that, we have the concept of average velocity. Average velocity is the average rate at which a displacement occurs over time. If you remember from, say, pre-calculus class, an average rate of change of a function. So if I have some function f of x, and I'm looking at on an interval from a to b, the average rate of change of that function is the slope from a to b, right? So this is what we would call an average rate of change. And if I just apply that same principle here, the average velocity, which is the average rate of change of displacement, is just the amount of displacement or the change in position divided by the amount of time it took for that displacement to happen. The numerator here is measured in meters. The denominator is measured in seconds. So the units of the velocity are meters divided by seconds. The instantaneous velocity, which I'm usually just going to call the velocity, is the instantaneous rate at which displacement occurs. And so this becomes the limit as the amount of time for the displacement to occur goes to zero. And this is a derivative, right? This is the derivative of position over time. So dr represents sort of an infinitesimal displacement, and dt is the infinitesimal amount of time it took for that displacement to occur. And so this is the good old derivative from calculus, and there will be some examples in subsequent videos showing you how to do calculations with this. So if I have another trajectory, so now we have another object at positions 1, 2, 3, 4, and 5. And the average velocity is always going to point in the direction of the displacement from one position to another. So the units of average velocity are meters per second, so the length of this arrow relative to the path itself isn't super meaningful. But the direction will always be from the first position to the second position, or whatever two positions we are calculating the average velocity for. So to clarify that, let's say I was interested in the average velocity from position 3 to position 5. Well, the displacement, or sorry, position 3 to position 4. The displacement from 3 to 4 is just this vector arrow that points in that direction, and the average velocity is in the exact same direction. The instantaneous velocity isn't associated with 2 points, but always just one single point. And the instantaneous velocity is always tangent to the trajectory. And so that means that the instantaneous velocity is always pointing in the direction you're moving at the instant in time, and the magnitude of that is your speed. So speed is the magnitude of velocity. Okay. So that is velocity, and now we're going to move to acceleration. So you saw that in this trajectory, the velocity was changing over time, so it wasn't always pointing in the same direction. And so we need to account for that, and that is called the acceleration. The average acceleration is just the rate of change of the instantaneous velocity over time. And so the average acceleration would just be velocity at time final minus the velocity at time initial divided by time final minus time initial. And this ratio is meters per second over seconds. So if I were to calculate that out, a meter per second divided by a second is the same as a meter per second divided by a second over 1, which is the same as a meter per second times 1 over a second, which is a meter over a second squared. So acceleration is measured in meters per second squared, and it is the rate at which the velocity is changing. And just like with velocity, we have instantaneous acceleration, which is the instantaneous rate at which velocity changes. And that is just the derivative of the velocity with respect to time. Okay. So that is the basic terminology of kinematics. We're going to start by looking at one-dimensional kinematics, and I'm going to put that in a separate video. But this is the essential, most general kind of notation and terminology that I need, and we're going to specialize to the 1D case to kind of understand what's going on, and then we'll go to the two-dimensional case.